Bismillah ar-Rahman ar-Rahim. We are interested in the determinant formula for the volume of an n-dimensional parallelotope or parallelepiped. We have n linearly independent vectors in the n-dimensional space Rn, and the parallelotope is described by this set here. We have a linear combination of those linearly independent vectors where the coefficients are numbers between 0 and 1. In 2 dimensions, if n is equal to 2, this is θ1 x1 plus θ2 x2. Here we have 2 vectors, x1, and this is x2. And if θ1 and θ2 change over their possible range from 0 to 1, we will cover the points in this parallelogram. So this is the special case when n is equal to 2. Define the matrix Ym. It is a matrix of size n by m, and it contains as columns the vectors from x1 all the way to xm. So n here is a number from 1 to n. Let alpha j be the volume of the set, which looks like our set of interest, but the summation is only to j. So here we are constructing our set using only the first j of those vectors. Our interest is alpha sub n. This is the case in which we use all n vectors. Let's start by computing alpha 1. So this will be the volume when we make use of just one vector, which is x1. In this case, the volume is the length. It's the length of the vector x1, and that's it. So this is the L2 norm of vector x1. And the L2 norm can be written as the square root of x1 transpose times x1. If vector x1 has components x11, x12, all the way to x1n, then what we do to compute the L2 norm is to take the raw version of this vector, the transpose of this vector, and multiply by the vector. So this is x11 all the way to x1n. When we do the multiplication, we will get x11 squared plus x12 squared, and so on. And this is the L2 norm squared. So taking the square root, now we have the length of that vector. We can think of this inner product as a 1 by 1 matrix. And so the determinant of the 1 by 1 matrix, which is just a scalar, is the scalar itself. So here, let's write this x1 transpose x1 in this weird way, determinant of x1 transpose x1. Note that the matrix y1 is a matrix with just one column, which is x1. So we can also write the volume, which is the length in this particular case, as the determinant of y1 transpose y1. Now let's move to alpha 2. So this will be the volume when we make use of the first 2 vectors, x1 and x2. Now we have a parallelogram, and the volume is basically the area of this parallelogram. What is the area? We take the length of vector x1, so this is the length of the base, but then we need to multiply by the height. And the height is the length of the component of vector x2 that is orthogonal to x1. Suppose that we have v n-dimensional linearly independent vectors g1, g2, all the way to gv, and v is less than or equal to n. Suppose these are the columns of matrix G. Now, the matrix that is G times G transpose G inverse G transpose, this matrix is an orthogonal projection matrix. It is a matrix that if we multiply by a vector from the left, then it projects the vector onto the range of matrix G, or the column space of matrix G. If we have identity of size n by n minus this matrix, then this is an orthogonal projection matrix, an orthogonal projector that takes a vector in the n-dimensional space and projects it onto the subspace orthogonal to the range of matrix G. Those orthogonal projection matrices are symmetric. They have eigenvalues that are either 0 or 1, and they are idempotent. If we square them, then we get the same matrix back. So this is the idea that we use here. We want to project x2 onto the subspace that is orthogonal to x1. The matrix that we will use is identity minus, here, this is the general form of the projection matrix. In our particular case, G is just one column, which is x1. This n by n matrix is an orthogonal projection matrix. If we apply this matrix to x2 by multiplying by x2 from the left, then we get the component of x2 that is orthogonal to x1. This will be the height of the parallelogram. The L2 norm of x1 can be written as the square root of x1 transpose x1, as we did earlier. If we have an orthogonal projection matrix multiplied by vector alpha and we are computing the L2 norm squared, then like here, the L2 norm squared is P alpha transpose times P alpha. this is alpha transpose P times alpha. But for an orthogonal projection matrix, the matrix is symmetric. So B transpose is equal to P. We have alpha transpose P squared alpha. And a projection matrix is idempotent. So P squared is equal to B. And so this is alpha transpose P alpha. So the L2 norm squared of this vector here is this quadratic form. X2 transpose, then the orthogonal projection matrix, then the vector X2. And this is always the case if we have a vector multiplied from the left by an orthogonal projector. Since here we have the L2 norm, then this quadratic form appears under the square root, like we did earlier. We will do this apparently weird step. We write down each scalar, each one by one matrix as a determinant. So you have here the determinant of x1 transpose x1, and this quadratic form, I will write it as the determinant, and then we have x2 transpose times identity times x2, that's x2 transpose x2, and then we have, this will be x2 transpose x1, and then x1 transpose x1 inverse. This is just a scalar, and so this quantity here is just 1 over the L2 norm squared of vector x1, and then we have x1 transpose x2. We have a very important result regarding the determinant of a block matrix. If we have a block matrix A, B, C, D, and this block is square and this block is square, the determinant of this matrix can be written as the determinant of A times the determinant of the Schur's complement of A. And so this is the determinant of D minus C, then the inverse of A, assuming of course that it is invertible, times B. We can also write the determinant as the determinant of D times the determinant of the Schur's complement of D, which is A minus B, and then D inverse, assuming it is non-singular, and then here we have C. If we look here, we have the determinant of something, and then we have the same structure as the determinant of a block matrix. The product of these two determinants is exactly the determinant of a 2 by 2 matrix, in which the elements look like this. We have here element 1, 1 is x1 transpose x1. Element 2, 2 is x2 transpose x2. And then here we have x1 transpose x2, and here we have x2 transpose x1. If we apply this general rule to compute the determinant of this 2 by 2 matrix, what we will do is that we will say that this is the determinant of x1 transpose x1, and then times the determinant of its Schur's complement, which is x2 transpose x2 minus, then we take this guy, x2 transpose x1, and then we take the inverse of the L2 norm squared of x1, and then we multiply by x1 transpose x2, which is exactly this determinant here. The product of these two determinants, using this result regarding the determinants of block matrices, can be combined as just one determinant of a 2 by 2 matrix. And now this 2 by 2 matrix can actually be obtained by taking a matrix with columns x1 and x2, then multiplying this matrix from the left by its transpose. So its transpose will be a matrix with 2 rows. The first row is x1 transpose, and the second row is x2 transpose. If we do this multiplication, we get x1 transpose x1, x1 transpose x2, x2 transpose x1, and then finally element 2, 2 is x2 transpose x2. And by the way that we have defined matrix Y, this will be Y2. This matrix is Y2. So the volume in this case, in which we use 2 of the vectors, so we are talking about a surface area, this is the square root of determinant of Y2 transpose Y2. We are now done with the simple cases in which we have used x1 alone and then x1 together with x2. We have obtained, if we use x1, that the volume is the square root of determinant y1 transpose y1. And when we have used x1 and x2, we get this result. If we assume that alpha k is the square root of determinant yk transpose yk, let's try to obtain alpha k plus 1 and check whether it can also be written down as the square root of determinant yk plus 1 transpose yk plus 1. What will be alpha k plus 1? So this is like an extension of the idea here. If we are now using k plus 1 vectors, so we take the volume when we use k vectors from x1 to xk, and then we need to multiply by the height. Generalization of this idea here. So we need to multiply by the L2 norm of the component of vector xk plus 1 that is orthogonal to the span of the vectors from x1 to xk. And what is this component? We take xk plus 1 multiplied from the left by this projection matrix. This is the matrix. Here we are using yk. Again, this matrix alone will project orthogonally onto the range of yk. This matrix projects onto this span. Identity minus this matrix will project onto the subspace that is orthogonal to the range of yk. If alpha k is the square root of determinant yk transpose yk, then what is this L2 norm? the L2 norm squared of an orthogonal projector times the vector is this quadratic form. The vector transpose times the orthogonal projector times the vector. So we do this here. The L2 norm squared will be the determinant of xk plus 1 transpose, and then our orthogonal projection matrix, and then xk plus 1. If we do the multiplication, we will get xk plus 1 transpose xk plus 1, and then we have minus xk plus 1 transpose yk, and then we have yk transpose yk inverse. Note that this is a k by k matrix, and it is indeed invertible because the columns of yk are the vectors from x1 to xk, and those are assumed to be linearly independent. Then we have yk transpose times xk plus 1. We again make use of this idea here. Let's see what we have. We have the determinant of a matrix here times another determinant that looks like a Schur's complement. So the product of these two determinants is as if we are computing the determinant of a k plus 1 by k plus 1 matrix. This block here of size k by k is yk transpose yk. And then here we have xk plus 1 transpose xk plus 1. Here we have xk plus 1 transpose yk. And finally here we have yk transpose xk plus 1. From the rules of the determinant, we can combine this product of determinants into the determinant of this k plus 1 by k plus 1 matrix. And this matrix itself can be written as a product. If we take a matrix yk and append to it the column xk plus 1, this matrix that we have here is this matrix multiplied by its transpose from the left. We can check if we do the product that this is exactly equal to that. And if we take yk and append column xk plus 1, this is exactly yk plus 1. So indeed, the volume is the square root of determinant yk plus 1 transpose yk plus 1. This seems to be the working formula. This is how we compute the volume. And now if we use the n vectors from x1 to xn, then the required volume, which is alpha n, will be the square root of determinant yn transpose yn. Yn is the n by n matrix with those columns. And in this particular case, yn is a square matrix. It is n by n. Note that matrix yk is n by k, and it is not square if k is strictly less than n. But now if we have yn, that's a square matrix. And so the determinant of this product can be written as the determinant of yn transpose times the determinant of yn. And the determinant of the transpose of a matrix is the same as the determinant of the matrix itself. So what we have here under the square root is the determinant of yn squared. And so the required volume, if we use the n vectors, is the absolute value of the determinant of yn.